A polynomial function is a function that takes this form. F of x is equal to a sub n times x to the power n plus a sub n minus 1 times x to the power n minus 1, and so on, plus a sub 2 x to the power 2 plus a sub 1 x to the power 1 plus a sub 0. So this is a constant term where x is to the power 0. Okay, so what you should notice is that n is the power on the x. And we're going to define this n to be a non-negative integer, meaning it could be 0, 1, 2, 3, 4, anything like that. So as long as it's a non-negative integer. So let's say it's 5. So for example, an example of this would be f of x is equal to, these a sub n minus 1, they're coefficients. So let's write that down. This a sub n minus 1, and so on. These are real numbers. So they can be any real number. So a polynomial function would look something like this. 5x to the, let's say, to the 6th, plus 4x to the 5th, plus 3x to the 4th, minus 17x cubed, plus 2x squared minus a half x plus 3. So you can see what's happening here. I choose a non-negative integer, and this non-negative integer is 6, and we're going down a power, and we have some real numbers as the coefficients. This number n, the highest power, is also called the degree. And I'm going to write here that it's the largest power of x. So for this particular example I gave you, the largest power is 6. Now this term is a very special term, and we call it the leading term. So a sub n x to the power n is what we call a leading term. And why this leading term is so special, what we're going to do is we're going to learn how to graph things like this. You see this polynomial function here? We're going to learn how to sketch the graph. And the leading term tells us a lot about the graph. So if we define a function, y is equal to a sub n times x to the power n, this is called a power function. And it determines the end behavior of our graph. Of the graph of the function we want. So just knowing this piece will tell us what's happening at the ends of the graph, but not what's happening in the middle of the graph. And you're going to learn more about that in the regular pre-calculus videos. Right now, I just want you to be able to identify it. So what we're going to do is we're going to try to figure out if certain functions are polynomial functions or not. And then we're going to determine the degree, find the leading term, and find the power function that the function we're given is going to resemble. Okay, let's look at some examples. So here's the first example. I have f of x is 5x to the 12th plus 6x to the 11th minus 10x to the 4th plus 2x squared minus 3. Is this a polynomial function? Again, compare it to this function here, which is the definition of a polynomial function. And recall that these coefficients are real numbers, and those real numbers can include the number 0, okay? So looking back at what I have here, notice that the highest power I have is 12. All the other powers I see are non-negative integers. So I have a 12, 11, a 4, a 2, and this one has a power of 0 on the x. This is a polynomial function. I'm going to abbreviate it to POLYN because I don't want to write it so much. Polynomial function. The degree here is 12. That's the largest power I see on an x. Also, I mentioned that we don't see some terms that some of the coefficients can't be 0. Notice that this is not written exactly in this state because you can see each time I have an n, which is 12, I subtract 1. So I should have an 11, a 10, a 9, an 8, all the way to 1, x to the power 1, and then the constant term. Here I have a 12, 11, but where's the x to the 10th and the x to the 9th? Well, all of those have coefficients of 0. So another way that you can write this is 5x to the 12th plus 6x to the 11th plus 0x to the 10th plus 0x to the 9th, and so on. I'm not going to finish writing this, but you can see that I would also have a 0x cubed and a 0 times x. And because we can write it in this form where we can plug in zeros for the missing terms, then it's a polynomial function. So it is a polynomial function. We have the degree. We're going to determine the leading term. And the leading term is the term in the polynomial that has the highest power, which is this one right here. So it's 5x to the 12th. And that's going to tell us that the power function that this graph resembles is y is equal to 5x to the 12th. And you're going to see that graphing something like this, 5x to the 12th, is going to be very easy, and it's going to be much easier compared to graphing this. So again, the power function, what we'll learn is it determines the end behavior of the graph, and the middle part is determined by all of this other stuff here. Let's look at the second problem. Here I have g of x is equal to 1 over 5 x to the 8th minus x to the 7th plus 1. Is this a polynomial function? Well, the answer is yes. This is a polynomial function. Notice that the degree is 8. Again, we have a degree 7, and anything less than 7, we can just add a 0 in front of that x to that power. So we can write this as, plus 0x to the 6, and so on, all the way till we get to 1. And this number in the front, it is a fraction. But remember, the coefficients in front of the x's, they can be a real number, and fractions are real numbers. So we found the degree. We also need to find the leading term and the power function that is attached to this graph. So the leading term is 1/5 x to the 8th, which tells us that the power function is y is equal to 1/5 x to the 8th. Here's the next function I want to show you. This is h of x is equal to 3 minus x squared. This is a polynomial function. The n here, the degree, is 2. Notice that h of x can be written like this. H of x is equal to negative x squared plus 3. I wrote it in this reverse form because I wanted to see if you could tell what the highest power of x was, and just notice that it's a polynomial function. So the degree is 2. That is the largest power on any x I see. And notice that it's a quadratic, and we actually know how to graph this function. This is the parent function of x squared, which is a parabola, flipped upside down and then moved up 3 units. So the leading term is negative x squared, so the power function is y is equal to negative x squared. And again, we could expand this if we wanted to put it in that polynomial form, where we have the degrees, the powers going down 1 unit each time we go out a term. Okay, here's the next problem. K of x is equal to 1/2 x plus the square root of 2. This is a polynomial function. In fact, this is a line. Notice that this takes the form ax plus b. So this is k of x. So the slope here is 1/2, and the y-intercept is the square root of 2. 1/2 and square root 2, they are real numbers. And this power on the x is 1. So the degree here is 1. And I could put this square root 2 here, as long as these coefficients are real numbers. So you have to know what a real number is. So fractions are real numbers and square roots are real numbers. So this is the normal form of a line. And you can also say that this looks like a sub 1x plus a sub 0, where the b, the y-intercept, is your constant term. Okay, the leading term is 1/2 x. So the power function that's attached to this is y is equal to 1/2 x. We already know how to graph this. We know how to find the y-intercept and then use the slope to finish this line. Here's another line, j of x is equal to 5. This is a polynomial function. In fact, it's just the constant term. So j of x is equal to a sub 0. The degree is equal to 0. And the leading term, well, there's only one term here, is equal to 5. So then the power function that's associated to this graph, you can think of it just being y is equal to 5. Okay, here I have some non-examples, and let's figure out why they're non-examples. The first one is f of x is 3 plus 2x plus x squared minus x to the negative 4th. All of the coefficients in front of these x's are real numbers. You have 3, 2, 1, and a negative 1. The issue is right here, this negative 4. Remember, I said that the powers on the x's have to be non-negative integers. This is a negative integer, so this is not a polynomial function. Let's look at the next example. We have g of x is equal to 5 plus x minus x to the 1/3. This is not a polynomial function. Why is it not a polynomial function? For a similar reason as the other one, we have a problem with one of the powers. This power, although it's not negative, it is not an integer. This is a third, and an integer is a whole number, right? So that's not a polynomial function. How about this one? H of x is equal to 3 plus x squared over x to the 4th plus 2x minus 1. Notice that on the top of this fraction, I have a polynomial. And on the bottom, I have a polynomial. But I'm dividing a polynomial by a polynomial. When you have a division sign, that doesn't have to do with a coefficient. when you have x's over x's, then this is not a polynomial function. We will learn about these types of functions later on in pre-calculus. Before I move on to the next section, I want to talk about another type of function you might see. I don't think we've seen it yet. And it would look like this. So let's say k of x is equal to 3 plus the square root of x minus 7, something like this, or something involving x under a square root. This is not a polynomial function. If you see square roots, then you're not going to have a polynomial function if the square root involves an x underneath it. Now, if the square root has just a number underneath it, well, that's okay, because that's a coefficient. But you can't have x's underneath a square root. You can't have any kind of polynomial under a square root. And actually, this is the same thing as x to the 1/2. So this is kind of like the problem we saw right here, because we can write this as the cubic root of x. But yeah, so if you see fractions involving x's, if you see roots involving x's, and if you see, there's another example, so fractions, roots, and negative integers. But that also corresponds to fractions, because x to the -4 is the same thing as 1 over x to the 4th. All of these things would imply you do not have a polynomial function. Okay, so a major topic in polynomial functions is graphing. And to graph a function, we usually find the roots of a polynomial function. Sometimes we'll be given all of the roots of the polynomial function, and it'll be really easy to have an idea of what the graph looks like. Sometimes we won't be given all the roots. We'll be given just the polynomial function in unfactored form. So what I want to do is I want to look at some examples of polynomial functions, and then I want to determine the maximum number and the minimum number of real roots for each one of the functions. So we're going to start with that. So here's my first function. F of x is 3x to the 5th plus 2x to the 6th minus 3x plus 7. When you want to figure out how many real roots you have, you want to find the degree. Now, I kind of mixed up these terms. Remember, the degree is the largest power of x. So the largest power here is here. So the degree is 6. And this is an even number. So what's going to happen is, when you factor something like this, you can have a maximum of 6 real roots. Remember that when you have some kind of polynomial, we've seen this, especially with like quadratics, for example, with x squared plus 1, this function here didn't have any real roots. If you remember what the graph looks like, is the parabola shifted up 1 unit. And in this case, we had complex roots. So you can either have real roots or complex roots, or a mixture of both. And we also learned that complex roots come in pairs. If we have a complex root, then we also get the complex conjugate root. So like this one, this has 2 roots. It has I and negative I. If you plug that in, either one of these, you'll get -1 plus 1, which will give you 0. And these are complex conjugates. So the maximum number of real roots we can have for a function with even degree is that number right here, the degree 6. And then we could also have complex roots. So it's possible that this function could be completely factored and we would get six real roots. Some other options would be we would get 4 real roots and then 2 complex roots. Now these don't have to be distinct roots. They could be repeated roots, but every time we lose a root, we have to lose 2 roots, because if we lose 2 real roots, then we would gain 2 complex roots, because we'd have to have complex conjugates. So we could also have 2 real roots and 4 complex roots. And the last option would be 0 real roots and 6 complex roots. So this would be the minimum number of real roots right here. So it's possible if we tried to factor this. Now, I don't know what would happen, at least not at this moment. We could try to factor it, but some things that could happen is we could get 6 real roots, and we could get repeated roots, but they would all be real. Or we could get 4 real roots and 2 complex roots. We could get 2 real roots and 4 complex roots. And then the smallest number of real roots we could get is 0 real roots and 6 complex roots. So whenever we have an even degree, the minimum number of real roots we could have is 0. And the maximum would be that degree. Let me change this to 9 here. So here I have another polynomial function, and I want to figure out the maximum number of real roots and the minimum number of real roots. So the maximum number of real roots is always going to be the degree. So we could have 9 real roots and 0 complex roots. But it's also possible that we have complex roots. So we could have, and remember these complex roots come in pairs. So we could have 7 real roots and 2 complex roots. We could have 5 real roots and 4 complex roots. We could have 3 real roots and 6 complex roots. Or we could have 1 real root and 8 complex roots. But since we can never have just an odd number of complex roots because we always have pairs, this would be the minimum number of real roots. So whenever you have a function of odd degree, so the largest power is odd, the maximum number of real roots you can have is that degree, and the minimum number of real roots is 1. So even, the minimum is 0, odd, the minimum is 1. Okay, so in section 3.2, we're actually not going to do that section this week. We're going to work on it next week. And what we'll try to do is factor something that's a polynomial function like this one right here. And sometimes factoring can be difficult. There's going to be a theorem that's going to teach us how to factor something like this. And that is going to be a little complicated. I mean, finding the potential factors is not too bad, but then actually determining if it's a factor or not is a little complicated. So I want you to at least to be exposed to figuring out any possible rational roots. So for example, here I have a function, and let's say I ask you to factor it. You might look at this and say, I don't even know how to start. How would I factor something like this? Well, what you're going to do is you're going to look at the degree of the function, which is 6. In fact, let's rewrite this so this is in the front. So this has degree 6. And we're going to look at the leading coefficient. So this is the leading coefficient, and this number back here is the constant term. Now this is really interesting. Remember that when you factor something, let's talk a little bit over here. Let's say I wanted to factor f of x is equal to x squared minus 1. Well, this is something we know how to factor. It factors into x minus 1 times x plus 1. But here I have a power of 6, and I really don't know how to factor this. So what you're going to do, at least to find the potential rational roots, that means numbers that are either integers or fractions. So we're not going to be able to find things that are like square root roots, so nothing like the square root of 5. We're just going to get fractions or integers. What we're going to do is we're going to take this constant term, which is a sub 0, and we're going to divide by an and put it plus minus. And all the factors could be our potential, let me erase that and say our potential roots. So let's find them, and then I'll explain with something that we're more familiar with. So you can see I have 7. So what I'm going to do is I'm going to put plus minus 7, and then I'm going to divide by this number here, which is 2. Remember, this is a sub n, which n here is 6, and then this is the constant term, which we're putting here. So all my potential roots, my rational roots, are going to be factors of 7, which is 1 and 7, and factors of 2, which is 1 times 2, and put a plus minus. So I can do 1 over 1. So 1 over 1, which is just 1. I could do 1 over 2, so 1/2. I could do 7 over 2, so 7 divided by 2, or 7. These are all the potential rational roots, but we also have a plus minus. So 1 or negative 1, 1/2 or negative 1/2, 7/2 or negative 7/2, or 7 and negative 7. So when we try to factor this, we could have something like x plus 1 times x minus 1/2 times x minus 7. Let me show you with this example, because we know how to factor this. This is x minus 1 times x plus 1. Here, let's look at the an term. The number in front of the x squared is just 1. This number back here is negative 1. So what we do is we take a0 over an plus minus. So the signs really don't matter here, but this is plus minus negative 1 over 1. So the only potential roots we have are 1 and negative 1. You can see that those are the only factors, and that turns out to be correct. Let me show you another example. So let's go with f of x is x minus 2 times x plus 3. I'm going to FOIL this out. So we get x squared, we get plus 3x minus 2x minus 6, which is x squared plus x minus 6. So this is the same function, just in a non-factored form. Now to find the roots, let's say we didn't know how to factor this. We want to know what could be a root, what could be a rational root here. So what we would do is we would take a sub 0, put a plus minus in the front, and divide it by a n. So you can see that I have a negative 6, so we can put plus minus. You don't even have to worry about that negative because you have a plus minus in the front over plus minus 1. Well, 6 is the same thing as 1, 2, 3, and 6. All of these are factors of 6. So 6 is divisible by 1, it's divisible by 2, 3, and 6. And then we have this plus minus in the front, and 1 is just divisible by itself. So the potential factors are plus minus 2, plus minus 3, or plus minus 6. So one or more of these numbers would be a factor of this function. And we know what those two numbers are. They're 2 and negative 3, which show up here. So not all of them are factors, but if we wanted to find all potential ones, then it would be one of these in here. Okay. So again, you'll see more of this in section 3.2. I just want you to have a starting point, just to see some of this, be familiar with it, and know what we're doing. Here's my second problem. I have g of x is negative 4x to the 8th plus 2x to the 7th minus x to the 6th plus 5x cubed plus x minus 10. What we want to do, let's remember what we're trying to find. We're trying to find all potential rational roots. So if we wanted to factor this, we want to know what the factors could be. So what we're going to do is we're going to take a sub 0 and divide it by a sub n and put a plus minus here. So this is equal to plus minus negative 10 over negative 4, which is plus minus. Both of these are divisible by 2. And this plus minus kind of cancels these out. You don't have to worry about that sign. So now let's write all the factors of 5. Well, that's just 1 and 5. And the factors of 2 are 1 and 2. So all potential roots are plus minus 1, plus minus 5, because I have 1 over 1. Then I have 5 over 1. And then I have 5 over 2 and 1 over 2. So those are all the possibilities when it comes to rational roots. I think I have one more. It looks like 2 more. Okay, 2 more. What are all the possible roots for this one? I think I want to try to make something a little more complicated. So I'm going to put a 10 in the front of this one. Okay, so h of x is 10x to the 5th plus 3x squared minus 2. What are all the potential roots? So we're just going to put plus minus negative 2 over 10. And we don't even need this negative, just drop it. Okay, so this is the same thing as plus minus 1 over 5. So our potential roots are 1, 1 over 5, and I think that's it, because this is equal to 1 times 1, this is 5 times 1. So 1 over 5 and 1 over 1. So we have 4 potential roots. I was hoping for something where we got more roots, but that's okay. Maybe we can do it with the next one. Yeah, let me see what I can change here. I'm actually going to make this number on the back. I'm going to make it an 8. Okay, so here's a function k of x is equal to negative 1/2 x to the 6 plus 3x squared minus 8. What are all the potential rational roots? Well, we're going to take this number, negative 8, put a plus minus in the front, and divide by this number, negative 1/2. So focus on this. This is plus minus. 8 divided by 1/2 is actually 16, right? Because you flip and multiply, and then the negatives cancel. But again, you don't have to worry about the negatives because you have a plus minus here. So we get plus minus 16, or plus minus 16 over 1. 16, let's break it into all of its factors. What are the numbers that divide 16? It's 1, 2, we've got 4, 8, and 16. I think that's all of them, because 16 is 8 times 2, and 8 is 4 times 2. So this is 2, 2, 2, 2. So you can see I get 4 times 4 makes 16. So all of these are the numbers that divide 16. And here I have a 1. Now if I had something more complicated down here, like let's say I had a 2 down here, I'd have to put 1 times 2. Or I could have something like, if I had 10, I would put 1, 2, 5, and 10. And so I would get a lot more answers here. You can see that I'll get plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and plus or minus 16. So those are all my potential roots. And again, if I had something else down here, let's say that this was a 5, and maybe I even had a 10 here, then I would have to do plus or minus 1, but also 1 over 5 and 1 over 10, then 2 over 1, 2 over 5, 2 over 10, 4 over 1, and so on. So I'd have a lot of roots. Because I only had 1 here in the bottom, that's the reason I got these 5 numbers here. There's 10 possible roots in total because I have this plus and negative in the front.